Our next speaker is going to be Thanasis Yanetsos, who can obviously do his own name much better than I can. His talk is titled SpySense, a spyware tool for executing stealthy exploits against sensor networks. Thanasis, it's all you. Turn your microphone on.
Yep. Hello, everyone. Thank you all for coming. Okay, so my name is Thanasis Yanetsos. It's a Greek name, so it's pretty difficult to pronounce. Today, I'm going to present SpySense, which is a spyware tool capable for executing stealthy exploits against sensor networks. It is a joint work between myself and Tassos Dimitriou, which actually sits over there. So, what is SpySense? SpySense is a tool that allows both the injection and activation of stealthy exploits in the nodes of a sensor network. Once activated, it is undetectable, it is hard to recognize and get rid of, since it remains idle in a portion of the memory region in the host sensor. Also, when activated, it runs in a discrete mode, so without interfering or disrupting the normal network operation. So actually, it operates in a complete stealthless mode. But before we go to the tool, we are going to say a few words about wireless sensor networks, their characteristics. Why are they so important, especially in current days and the new application domain they are currently being used, their security challenges, and what motivates us to build such a tool like SpySense. Also, we are going to overview the platform that we are going to be using for our demo, which is the Timot Sky. So starting, distributed sensor networks are heterogeneous systems consisting of thousands of low-cost and low-power tiny sensors that are interconnected by a communication network. As you can see, each one of the sensor devices contains a small CPU, a radio wireless transceiver, a memory storage unit, and the ports, the actual sensors, that are capable of sensing and interacting with the physical environment. There are a lot of example platforms that are currently being produced by various companies, depending on the application they are going to be used. We have chosen the Timot Sky as a concrete example, because all the vulnerabilities that are explored in this kind of hardware also exist in other platforms. The important thing is that sensor nodes remain simple embedded devices with radio capabilities. So actually, the incorporated microcontroller has extremely limited resources because they want to operate for a large period of time, usually featuring an 8 or a 16-bit RISC processor, and following either the von Neumann or the Harvard architecture. But the bottom line is that they are still a computer. So all the existing vulnerabilities of embedded devices come into practice for sensor nodes, and they are even more destructive as they are usually overlooked in the design of sensor network applications, because security developers, what they do is that they look, instead of looking the sensor network as a collection of small computing devices, they look the network as a computer in itself, and they are trying to secure it against attacks that target upper layer, the transportation layer, the routing layer, the MAC layer. So they skip the fact that sensor network still comprise of embedded devices. Now, embedded systems are not new, but sensor networks take them to a new level. They are self-configuring systems, so their position when deployed must not be predetermined or engineered. And once deployed, they can operate for large period of times without being interrupted. Some of the most popular features of this kind of networks is that they are redundant, they use redundant paths. So actually, we can use this in order to deploy fault-tolerant systems that they degrade gracefully in the case of extreme circumstances, like node crashes, link crashes, or node shifts. Also, one more attribute of these networks is their cooperative effort. So actually, sensor nodes can detect multiple inputs. You can have some portion of the sensor nodes detecting something and some other portion of the sensor network detecting something else. Combining such values, they can produce information that cannot be sensed directly. So actually, they cooperate with each other in order to aggregate the information that they are going to send to the base station. Up until now, very popular applications are the smart grids. They're used in military applications, wildlife monitoring, environmental monitoring, structural monitoring, and the so-called smart environments, okay, where they put the sensor nodes in a home, the so-called smart home. They connect every device in the internet, so wherever you are, you can turn on your PC, your air condition, anything like that. However, the current trend is moving from statically deployed sensor networks where users are passive data consumers, okay, to one where people will carry sensing elements involving the collection, storage, processing, and fusion of data related to everyday human activities. So actually, this is the application that they were expecting to be the killer application for sensor networks, and it is expected in the next year to be really popular. What they do is they integrate the sensor into mobile phones and PDAs. That's why this application was driven by the involvement of such devices and their growth in usage by peoples. But it is obvious that we need more robust security mechanisms because we have to deal with extremely large volumes of data, and then we also have to take into consideration privacy and ethical issues regarding the users that provide their mobile phones. So actually, we have to convince them to allow us to use their equipment as part of the sensing infrastructure. So the vision is by having wireless sensor network, wireless sensors to the hands of thousands in order to be able to deploy human-centric sensor networks for solving urban-scale problems, for example, like public health monitoring. There is a number of such projects, like CitySense, NoiseTube. For example, the first one I think that it was produced is the BikeNeck, which is a project for bicyclists. So actually, they use the sensor inside the mobile phones, and each one of the bicyclists that goes to an area, it monitoring the temperature, the humidity, the sun, and they communicate with each other in order to say to other bicyclists, okay, this is a good area to go for your ride, this is not a good area, and so on and so forth. However, again, it is obvious that we need very good security mechanisms because instead of having to look only for the vulnerabilities that arise from the sensor networks, now we have to take into consideration other kinds of vulnerabilities that come into play from the mobile phone. Okay, so it is easy maybe to hack the mobile phone and get access to the information transferred within the network. Okay, so sensor networks are really important. They are popular. They are used in various kinds of applications, and they are expected to be popular like the internet. But what are the security requirements? Okay, it's pretty straightforward. Their security profile follows the profile of any type of networking: confidentiality, authenticity, integrity, data availability, freshness. And there is a set of secondary goals which arise from their attributes. So actually, they have to provide self-organization in order to be able to create some trust relationship schemes between the nodes in order to exchange keys between the nodes. Then we have time synchronization because they have to operate in low power mode. Most of the time, they are sleeping, and the nodes wake up when they want to transmit something. We have secure localization, and the most important is secure data aggregation, because the traffic inside the sensor network is extremely high. So each node acts as a router, aggregates the data, and then forwards to the next hop until it reaches the base station. The security challenges. Now, because they are using the wireless medium, they are transmitting over there, okay, obviously, they are susceptible to attacks like eavesdropping, interception, alteration, replay, or injection of malicious packet. Now, also, as we said, the microcontroller has extremely limited resources. So every kind of security mechanism and protocol that is implemented and is going to be stored in the node cannot consume a lot of power and or CPU cycles. So that's why public key cryptography is out of the picture. In sensor networks, we are only using symmetric keys, which is not that good. Also, since they are deployed in hostile environments and they are operating unattended, it is pretty easy for someone to capture a node, attach it to a PC, and then extract the program image running inside, or the keys, and all this stuff. And it's pretty difficult to protect against insider attacks because it is impossible to have a person guarding each one of the nodes deployed in the network. Finally, because once deployed, they deployed randomly. The administrator of the network does not have a clue of where is the position of each node. So if an attacker goes there and pick up the node and put it somewhere else, so okay, what happens? Nobody knows. These are some of the most important attacks. Okay. As we said, eavesdropping, data replay, select forwarding. Against the routing layer, these are attacks that are trying to get access to the information transfer within the network. Sinkhole, wormhole, hollow flood attack. These are extremely dangerous and are pretty difficult to protect against. But up until now, several defense mechanisms have been proposed against specific attacks. However, security holes always exist. Attackers can always find ways to bypass the current existing security mechanisms or find new ways of performing these attacks, again, to bypass all the security protocols. Researchers have moved on to implementing and creating intrusion detection protocols that instead of trying to detect specific kind of attacks, they are trying to detect any abnormality in the traffic transferred within. So the goal of these intrusion detection protocols is to withstand attacks that have not been anticipated before. So actually to observe any pattern that arises from an attack or their signature and all this stuff. However, our motto is that how can someone build an efficient intrusion detection protocol if up until now no one has discovered all the network vulnerabilities that come into play into sensor networks? Okay. So that's why we believe that better understanding of network and hardware vulnerabilities enables the design of more resilient security mechanisms. This can be done in two ways. So first of all, practice the best ways to perform existing attacks and study new threat models. That's why this is what we are studying. So in the first case, we have produced a tool called Sensis. We have presented it in BlackHat 2010 in Europe. You can check out the link. So this tool is actually it's capable of performing various kinds of attacks against sensor networks: sinkhole, wormhole, replay, data injection, hollow flood attack, zombie attack. All these kinds of attacks are provided by this tool. And the way that these attacks are performed are the best way, so they can bypass most of the existing security mechanisms. So continue our work on studying these vulnerabilities. We have started to study new threat models. So actually, we saw the sensor network as a set of embedded devices. Okay, so we tried to target each one of the sensor nodes. That's why back in 2010, we started to look into software attacks that try to take advantage of memory-related vulnerabilities. We performed malicious code injection back in 2010, and we created the first instance of a sensor worm. So actually, by injecting malicious code into a node and activating this code replicates itself, rebroadcasts itself to all the neighboring nodes, and by affecting one node, you can actually take control over the entire network. Now, in this tool, we move to one step further, and we will show how can someone take advantage of these malicious code injection attacks in order to inject spyware exploits in the sensor nodes of a network. Our goal is not to show how to find memory-related vulnerability. Okay, I think it's not that easy, but it's pretty obvious that you need a vulnerability in order to perform like a buffer overflow, to perform malicious code injection. Okay, moving on to show the T-Mode Sky platform. This is the platform that we're going to use in our demo. You can see it over here. This is the T-Mode Sky. So first of all, a brief review between the differences in von Neumann architecture devices and Harvard architecture devices. Actually, the difference is that in Harvard-based sensor devices, the code and data memory are physically and logically divided. So actually, the program counter can only execute instructions residing in the code memory. Okay? You cannot manipulate the program counter to point in the data memory, so to actually execute instructions residing in the data memory. In the von Neumann architecture, in contrast, the program counter can go anywhere. So actually, if you store instructions in the data memory region of a sensor node, you can tell the program counter to go there and execute all your instructions. The T-Mode Sky follows the von Neumann architecture. And as you can see, it has 10 kilobytes of RAM, 48 kilobytes of flash code memory. Now, this is an overview of the memory map inside the node. Okay, we used the JTAG interface in order to extract the exact addresses. The important thing here is that because sensor devices are really sensitive when coming to executing code instructions inside their memory, they have to reside in consecutive memory blocks. That's why the lower RAM is actually mirrored to the upper RAM. So we have actually one memory region that is stored for executable RAM. And inside there, we have the stack and the heap, so these are well known. However, again, in sensor networks, no dynamic memory allocation is supported. Okay, so the heap memory in embedded devices is reserved for this reason. That's why in the mode and in all devices, despite the von Neumann or the Harvard architecture, the heap memory region is empty, okay, and unused. Because they don't use dynamic memory allocation. All memory addresses reserved for function interrupt handlers are created and linked when the program is compiled. Okay. Okay, so then the other things are pretty obvious. As in all embedded devices, we have the bootstrap loader, we have the interrupt vector. So the interrupt vector contains the handlers for receiving the messages, for the sensing, okay, the actuators for the sensors and all this stuff. Now again, we chose this platform as an example. Okay. All the vulnerabilities in here can be found in other devices. Okay. It does not depend if it follows the von Neumann or the Harvard. Okay. This different, okay, makes a difference in the way that the code injection will be performed. Now, in our toy application for this demo, we have the nodes running the Delta application. It's a pretty popular application in research sensor networks. What they do is periodically, every 10,000 milliseconds, so every 10 seconds, they wake up, they monitor the temperature, the humidity, okay, they put in a packet and they broadcast it in order to reach the base station. We have also implemented so that each one of the nodes generates a one key chain, hash key chain, consisted of 5 keys. So every 30 seconds, they produce, each one of the nodes, a new key chain. They use these keys for encrypting the messages and signing the messages. Okay. This will be used for showing the data retrieval exploit in order to show how can someone use the SpySense in order to retrieve all the keys used for signing the messages. Okay, so actually now we'll move on to the actual tool. So Spyware tool, as we said, allows both the injection and activation of stealthy exploits. It is based on memory-related vulnerabilities in order to perform code injection attacks. It is undetectable, and once activated, it runs in discrete background mode. Exploits are actually sequences of machine code instructions that are sent through packets and executed in the host sensor. Now, predefined exploits in the SpySense tool are these ones shown here. So we have data manipulation exploits, data theft, and data alteration. These are the most important because they can be used for altering data variables, keys, data structure inside the node's memory, and the data theft can be used for retrieving private and sensitive information, like especially keys. Or if you're combining with the new application domain of participatory sensing, this data theft exploit can be used for retrieving information that has to do with the mobile phone and the owner of the mobile phone. Okay. Who is the owner, its location, and so on and so forth. The second kind of exploits are the cracking exploits. So we have the extensive resource usage exploit. So once activated for a certain period of time that you define, the sensor node will be in an extensive resource usage mode. It will consume CPU cycles without doing anything else. Then we have the ID change exploit. Okay. So once deployed, all the nodes have one specific ID. Okay. Actually, these are like the IP addresses we are using in the internet. So because every node reports data back to the base station and eventually the administrator has to know from which this data comes from. So that's why we have the IDs. With the ID change exploit, we can change on the fly the ID of the node. Okay. Now this can be used for performing other kind of attacks, like the zombie attack, which actually this means introducing into the network nodes that actually do not exist. Okay. So eventually, if you use this kind of exploit with tools like Senses, okay, you can completely take control over the network, destroy it, put your own program image, do whatever you like. Finally, we have the network damage exploits, which when performed, okay, they will have a destructive effect on the network. We have the radio communication breakdown. What this does is it tells the node to stop transmitting, okay, but only transmitting. It can receive, but it cannot transmit messages. Okay. It thinks that the radio transceiver has something, something wrong, so I cannot transmit. Okay. Also, the node itself thinks that it cannot receive, but actually it can receive, because the handler for receiving is stored in the interrupt handler vector, and the handler for transmitting is stored in the flash code memory. So the event handlers for these two events of transmission and reception are separate. So it's not necessary to know the one event handler what is happening with the other. And finally, we have the complete system shutdown. Okay, so there is a function called stop program execution, which is stored in every embedded devices. Okay. This is actually the function that is called when you tell the embedded device to stop, to shut down. So if you want, you can tell the program counter to go there, and the sensor node will stop operating. And especially for this exploit, once performed, you cannot reset the node on the fly, okay, by sending a message. You have to hard code it, go there, get it, and push the reset button. Okay, so it's pretty difficult, especially if you deployed it in environments that cannot be accessible by humans. Now we are going to talk about how it works. Okay. The intuition is to take advantage of memory-related vulnerabilities, like unprotected buffers that may lead to stack overflow, format string specifiers, so on and so forth. So what we do is send specially crafted packets that contain the exploit, the machine code instruction, and these are copied to the memory region of the host sensor. And remember that in embedded systems in general, malware is pretty common. Everyone looks for it, and they don't want it. But in sensor networks, because as we said, they don't look at them as embedded devices, malware is rare, no one looks for it, and malware in its simplest form, okay, will go undetectable. Okay. Now, the most important thing again here that we take advantage, okay, in sensor networks is that the compiler produced single statically linked program images. Okay, what this means is that once you have a program image downloaded to one sensor, the same program image will be downloaded to all of the nodes in the network. Okay. So actually, if you have your hands on this program image and you find the memory addresses for receiving a packet, the memory addresses of where the transmission function is, okay, the same addresses will be for the entire network. Okay. Again, this is a pretty big bug of sensor networks. Now, a little bit of a history. Okay, Travis Goodspeed, which actually here in the conference, was the first to offer a wireless sensor network exploit. He showed how to perform a buffer overflow attack in order to execute instructions within received packets in devices following the von Neumann architecture. So he was the first one that showed that the memory buffer used for receiving packets is the same for the entire network. So you can actually manipulate the program counter to point into the instructions within a received packet and actually perform the instructions. Now, these two guys from France that I will not try to pronounce their names because I will kill them, demonstrated how code injection can be performed on devices following the Harvard architecture, okay, which is more challenging because you cannot store instruction in the data memory region and then tell the program counter to go there. What they did is they created gadgets of pre-existing instruction inside the memory of a node, and then they were able to call these gadgets in order to install a new stack. Okay. This was done byte by byte. So once the new stack is installed, then they can use the stack in order to inject malicious code or a new firmware. The bad thing with that is that it takes a lot of time. Okay. Since injecting byte per byte a new firmware and a new stack. If you do that, you might be detected by the administrator of the network. Now, based on these code injection attacks, as we said back in 2010, we authored the first instance of a self-replicating worm. Okay, so we used this technique of sending malicious code instructions through a message stream container in one node of the network. Okay, once injected, this shell code replicates itself, uses the radio of the sensor node to rebroadcast itself, hop by hop, and eventually the attacker will have control of the entire network. Once it replicates itself and rebroadcasts, then the attacker can have another shell code of doing so. For example, he can put another program image. So then the worm will replicate this program image to the entire network. Eventually, the attacker will have the network doing what he wants. The same thing as we said before exists here. So once the worm is injected, okay, you cannot delete it by resetting the node on the fly. You have to go there, pick it up, and reset it, hard-code it. Now, as we said, we move one step further, and we saw how to use such a code injection technique, okay, to store anywhere in the mode's memory spyware exploits that cannot be detected. Now, these are the two questions that are important for injecting such exploits in the sensor network. How the attack code is sent and stored on sensor nodes, and where the attack code is stored. For the first question, okay, the obvious is that, as we said, you can send it as data payload of a message. However, in sensor networks, you cannot have unlimited payload inside the message. By default, this is 28 bytes. You can go up until 102 bytes, but this is where you can go. You cannot have bigger packets. But what you can do is you can break your code down into 28 bytes instruction and then send portions of the attack codes through messages. Okay. The important thing here is that once you send a message containing portion of your attack code, it is essential to restore the normal execution, the normal program flow of the node. Because if you don't do that, then you cannot send any other packets. Okay, as we said, sensor devices are pretty sensitive on how they execute the instructions. Now, where the attack code is stored, obviously, since the heap memory region is unused, it works as the perfect umbrella where we can put our exploits. Okay, no one will look for them in this memory region. You will not override existing code inside the node. Okay, so now these are the steps of performing the code injection of stealth exploits. Okay. First of all, the important thing is to understand the memory map of the device. You have to extract some important memory addresses, for example, the storage address of the malware. Okay, so to find a suitable memory address in the heap memory region from where you will start copying your code. Okay, so this memory region in the heap, eventually at the end, once the exploit is injected, will hold the whole exploit shellcode. The second thing is to find the memory addresses of existing functions that will be used by your exploits. For example, you will use in the data retrieval exploit the radio transceiver. Okay, so you have to find the memory address of where this function is stored. Okay, but this is pretty easy because all functions in sensor networks are inlined. Okay, so by using JTAG interfaces, checksum bytes, you can extract these memory addresses. Actually, what we have done is we have used a JTAG interface, and it's pretty easy for specific program images to extract these memory addresses. And as we said, once extracted, these addresses will be the same for the entire sensor network. Now, continuing, we transmit a series of malicious packets containing the exploit code, okay, as many as necessary for sending your whole attack code in the host sensor. We perform a multi-stage buffer overflow attack. Okay, so what this means is that when you send the packet, you have the unprotected buffer or any other kind of memory-related vulnerability. You overflow the buffer, you override the stack, you point the program counter to the instructions inside the packet, But the important thing is that when you finish executing the instructions inside the packet, you have to restore the control flow. Okay, otherwise, further reception of such kind of packets will not be possible. And finally, once ejected, you send a last message where you redirect the program flow in the starting memory address of your shellcode. Now, these are the steps illustrated in a figure. So the first step is when you send the packet, you have the strcopy function, which is very popular for leading to buffer overflows. Then you redirect the program counter inside the payload of your transmitted message. Okay. In the lower figure, you can see actually how the message is constructed. Okay. It contains 3 parts. The first part is for overwriting the return address in the stack, so actually doing the buffer overflow and redirecting the program counter in the instructions contained in the message. The second part, which is the heart of the message, contains move instructions, actually copying bytes of your attack code in the target pointer where you have selected, actually in the heap memory region. And the final part of the message contains move instruction and branch instruction for the program counter, so actually redirecting the program counter to where it's supposed to be before executing the instructions inside the packet, so actually getting the node back to its normal state in order for further reception of malicious packets. Now, once all these are done, what we have achieved to inject shellcodes that coexist with prior firmware. Okay, so we don't overwrite any of the existing code. We reuse the code of the victim once needed, only for exploits that have, for example, the data retrieval, we need to use the radio transceiver, or we take advantage of the multi-hop communication nature of sensor networks in order to reach the most distant nodes. We have a memory stealthiness trade-off, meaning that we can add some instruction in each one of the shellcode exploit in order to delete the signature of the exploit once executed. Okay, in order for the administrator, if it gets his hands on the node, to not be able to see the traces of the exploit. But as you can understand, we have to add more instructions, and then we have to use more memory. Now, this is important. This is the configuration properties that must be given to the tool before you use it. Okay. The important thing here is the 3 last ones. The exploit folder contains all the shellcode profiles that will be loaded to SpySense and then will be injected in the network. The exploit stack and program counter fix are the memory addresses used for restoring the normal execution of the victim. The exploit stack actually is when you override the stack and you manipulate the program counter. This is the memory address where it will go after copying your instructions to the heap memory region. And the program counter fix is once this is the final part of each one of the messages where the program counter should go. And the attack address is, as we said, holds the memory address where each one of the shellcodes will start to be copied. Okay. This will be the memory region of each one of the shellcodes. Now, this is the central page of the tool. Okay, we can show it also. Okay, so this is the tool. As you can see, up until now, we have 6 loaded exploits, the one that we said before. And we can see the okay, for example, this is the data injection. On the right, you can see the machine code profile of the shell code. This holds the instruction that will be sent, transmitted, and copied to the heap memory region of each one of the nodes. On the left, we see the assembly code profile of each one of these exploits. Okay, so actually, this one is for understanding what the shell code does, but we will see later on. Okay, the important thing is that once you start running the SpySense, it's pretty easy to do on-the-fly reconfiguration with newly defined exploits. Okay, that's why you have the change setting buttons, so you can give them new exploits. Now we are going to look into details about this shellcode the exploit, we are going to analyze the exploit profiles. Okay, so before doing that, the important thing is to understand this memory symbol table. Once you inject or activate an exploit, you have to give, as we said, some specific memory addresses. Okay, the first 4 must be extracted before system boot up, and you have to give them as configuration properties in the system. These are the ones that we talked about before. The rest are given as arguments in the exploits because, for example, in the data injection exploit, you say to the exploit shellcode, eject, overwrite some of the data. But you have to give them as an argument the actual data that will be overwritten in the sensor node. Likewise, at the data theft exploit, you have to tell it from where it will get the bytes and how many bytes it will transmit back to you. Okay, all this stuff are given as exploit arguments. Now, starting with the data theft exploit, okay, as we said, it reports back important or confidential information, 2 basic functions, retrieval of the selected data memory region, which you give as an exploit argument, and it constructs and transmits back to SpySense the appropriate reply message with the selected data. The important thing, though, it's without disrupting the victim's normal operation. Okay, so it sends back to SpySense the message only when it sees that the node doesn't have to do anything else. It occupies 140 bytes, so 30 packets will be needed by SpySense setup engine to eject the code. Okay, so this is the assembly profile of this shell code. So we can see that the first instruction set, okay, is being used for initializing the payload of the reply message that will be sent back to SpySense. It's pretty easy. Okay, I think most of you know the assembly language, so it's pretty easy. The second instruction set is for copying the retrieved values in the payload of the message. Again, from where it will get the data bytes, you give them as an argument. Now, the important thing is this instruction set where you tell the node to transmit it back. Okay. As you can see, instruction 26 calls the function of the wireless radio transceiver of the host sensor. However, the important thing here is that we call the function, so we let the node to tell its scheduler, I have to send something. Okay, we don't force the node to send it right away. We let the node to inform its scheduler, I have to send something that's legitimate. Once I can, I will send it. Okay, so we don't force it. That's why we don't disrupt normal network operation. Now, the final part is where we clear all the arguments that we have given. Okay, so actually, we don't leave any trace. These instructions are not necessary for the correct operation. What is necessary is the final instruction, which is the branch instruction. So every time you activate the exploit, it runs one time, and when the program counter executes this instruction, it restores the normal program flow of the node. Okay, so it goes back to doing what it was supposed to do. And because all these exploits are really fast, really quick, okay, you cannot, the administrator cannot detect that something is going wrong. The second exploit is the data theft exploit. Okay, the data alteration exploit alters the values of existing data structure and variables. So you tell it to the node that I want to change the data structure stored in this memory region, and you tell it, you give it the data that will override this structure. Okay. As we said in the beginning, it creates backdoor entries for adversaries to perform more direct attacks like sinkhole, wormhole, data replay, zombie attack, so on and so forth, because this kind of exploit is used as the basis for other exploits like the ID change and the radio communication breakdown. It occupies 56 bits, so 14 packets will be needed by SpySense setup engine, and you can either alter only 1 byte or the entire message stream, okay, for the incoming or outgoing traffic. Again, here we can see that this instruction set is responsible for copying the updated value to the targeted data structure. Okay, it uses 2 arguments, argument 1 and argument 2. Argument 1 holds the memory address that holds the number of bytes that will be overwritten, and the second exploit argument holds actually the data bytes that will overwrite the targeted memory region. And again, this instruction set clears the argument memory addresses and restores normal state. Now, moving on to the cracking exploits, this contains the energy exhaustion and resource usage. Okay, the energy exhaustion, once activated, okay, you cannot go back. It tells the node to start unnecessary communication until it drains all its energy out. Once this is done, then it calls this stop program execution function and it stops operating. Okay. So actually, this is done automatically because each one of the nodes, before transmitting a message, check to see if they have enough energy. If they don't have enough energy, they say, okay, I'm dying, I have to stop. So what you do with this kind of exploit, you start an infinite loop of unnecessary communications, okay, of transmitting dummy messages. Okay, you fill these messages with dummy bytes, okay, so in order to take much of the energy, because if you transmit an empty packet, okay, you will not use any of the energy. But if you transmit, let's say, 28 packets, the full message size, then you will, eventually it will drain all its energy out. It occupies 102 bytes, so 26 packets will be needed for injecting this kind of exploit. Then we have the resource usage. Okay. So what this does, it tells to the node to consume CPU cycles for a specific time period. The time period, again, is given by the user as an exploit argument. Now, this is the code for the energy exhaustion exploit. Okay. This instruction set is responsible for creating the dummy packet that is going to be transmitted. Okay. It copies a random sequence of data that can be found in the code memory region of the node. Okay. It's completely random from where it copies the bytes. Then, this instruction set is responsible for invoking the transmission function of the victim's local radio. Okay. You will see that this set is the same as the data retrieval exploit. The difference is in the next set, because we want the node to actually transmit the message at the time that we tell it to. Okay, so actually we want to force it to transmit the message at this time. That's why we call the run task routing of the underlying scheduler in order to transmit it at that time. And then we don't let it to go back to its normal state, but we keep transmitting messages until the node drains all its energy out. And finally, this is what we said, that the last instruction forces the node to shut down. This is a stop program execution. Okay, usually, this can be found in most sensor-embedded devices in this address, the B368. Okay. Now, this is the resource usage exploit. Okay, it's pretty simple. It actually contains two loops. The outer loop is always set to the highest possible 2-byte value, okay, the FFFF. The inner loop is actually contains the time that the node will be in this resource usage exploit, okay, in this extreme resource usage mode. Okay, by experiments, we have found that this is the equation for telling the node how much time to stay in this mode. As you can see, again, this is like the data alteration because you tell it to overwrite a variable inside the node's memory, and then it will be in this mode for as long as you tell it to. Finally, the radio communication breakdown exploits. Okay, this is pretty fancy because we are using, again, one of the vulnerabilities that are not found in the application layer of the node. Okay, they are found in the MAC layer. Now, what they are using, they have a variable called the B shutdown request. Okay, this is actually the variable that the node checks before transmitting a message. Okay, if you set it to 1, it is active, meaning that I can use my radio so I can transmit a message. If you set it to 0, this means that I cannot transmit a message. However, keep in mind that if you set it to 0, the node will think that you cannot transmit, that I cannot receive. But actually, it cannot only receive. It cannot transmit. It can receive messages. So what you can tell to the node through this exploit is stop transmitting, but you can again initialize transmissions for your own usage whenever you want, because the node can receive your own exploit messages. And this is pretty small, only 2 packets will be needed by SpySense setup engine. Okay, finally, through the tool, we give to the user the possibility to define her own new exploits. Okay, if they write the machine code profile inside the simple text file, and they put it in the root folder. Once the SpySense tool boots up, then it will load the newly defined exploit. Okay, now I think we'll go to the demo. Now, these are all the exploits provided by SpySense. Okay, as we said, these are the data injection, data theft, energy exhaustion, ID change, resource usage, stop radio. Okay, so for example, we can tell it to inject the data theft exploit into node 11. We will give them the attack address. So this is the memory address inside the heap region where the exploit shell code will be stored. Okay. For example, we can give them 2080. And the next three memory addresses are the exploit arguments that will be used by this shell code once activated. Okay. The first argument will hold the number of bytes that will be retrieved. The second memory address holds the actual address inside the node's memory from where we want to retrieve this data. And the third argument is actually the task ID, because we give the possibility, in order for activating yourself, to have a periodic task that sends activation messages every 10, 15 seconds in order to get back keys and other private information. Okay, so if we give 2000 as the first, okay, all these addresses are inside the heap memory region because we do not want to overwrite any one of the existing code. It actually, you have to be careful in order not to use addresses that reside in the stack. Okay. As you remember from the memory map of the T-mode, inside the RAM memory region, the stack grows downwards and the heap grows upwards. Okay, so if the program image running inside the node is pretty big, so the stack will be pretty big. So you have to be careful not to use memory addresses that are reserved for the stack. Oops. Okay, so now the tool has started to injecting this exploit shell code inside the node with ID 11. Okay, I don't think you can see it, but this node over here starts receiving all these specially crafted messages. Okay, upon reception of each one of the messages, portion of the attack code is copied into the heap memory region. Okay, the blue LED is turning on and off, but okay, I don't want to move them because if you move them, then you are going to start losing packets. But even in the case that you lose one of the packets, okay, you have to understand that the attack shell code must reside in consecutive memory blocks. Okay, because if this is not the case, once you activate it, the program counter will start executing all the instructions inside the heap memory region. Once it reaches a memory block that doesn't contain a valid instruction, it will reset itself. Okay, it will go into an unstable state. So obviously, you are going to be detected by the administrator of the network. But if one of the messages is lost by the node, there is no worry. SpySense will inform that, okay, one of the messages is not sent correctly, so you have to re-inject the whole shell code again. Okay. So now this was injected successfully, so we can go and activate the exploit. Okay, the node ID 11. Now we have to set up correctly the argument exploits. So you have to remember the memory addresses that you gave during the exploit injection in order to give, because once activated, the exploit will go and get the argument values from the memory addresses that you gave during injection. Okay, so in memory address 2000, we want 28 bytes. Now we are going to retrieve the keys inside the node's memory. Now, this memory address, 11.8a, okay, it's actually the memory address where the key chain of the node is stored. Okay. You can see that you have to know the memory address where this key chain is stored in order to ask it from the exploit to get it back. But as we said, it's pretty easy to extract these memory addresses because they are inlined, and you can make various attempts through this exploit and eventually find these memory addresses. And we give the ID 15. So we will start a task every 10 seconds. Okay, so we are start receiving back. So you can see here that the node sent us back the data that we requested. So actually, this over here, it's the key chain containing the 4 keys that were produced by the node. And you have told the SpySense to send activation messages every 10 seconds. So you will keep receiving the new keys that are produced by the sensor node for as long as you want. You see that we are receiving the messages. Okay. It's the same because they have not passed. Each one of the nodes every 30 seconds produces a new keychain. Okay. So for the first, I think, 2 attempts, it will get the same keys, but now it got the new keychain that was produced by the node. Okay. So eventually you get the keys that are used in each one of the time periods for signing the messages and authenticating and encrypting the messages. Now, if you use this exploit with the attack tool like Sensis that has a sniffer, and you can overhear all the network traffic, you can have the encrypted messages, you have the keys, so actually you have access to all the private information that are transferred within the network. And you can use data theft exploit in order to reach the most distant network node. Okay, so you can have access to all of the keys of the nodes inside the network. Okay, so we're going to leave it to run. Next, for example, we are going to show the data alteration exploit. Okay, so in order to show this exploit, how it works, we have to say that the Delta application, as we said, every 10 seconds, the node wakes up. Okay, it senses its environment, the humidity, the temperature, and then it reports back the information to the base station. So we can again activate the data theft exploit in order to see the value of this data variable that holds the time period of when the node wakes up in order to sense the environment. To see, and then we will change this in order to see this change. Okay, but first we have to inject it. One other thing here is that you have to be careful not to overwrite in the heap memory region the already injected exploits. Okay. So as you remember, the previous data theft exploit resides starting in the memory address 28. Okay. So you must be careful not to overwrite this existing shellcode. So we are going to give it space. Okay, so now the same procedure is being followed. We are sending 14 packets that are necessary for copying the whole exploit shellcode in the node's memory. And once finished, we are going to be able to activate it. Now, once ejected, you can activate it anytime you want. Once activated, it will run one time, and then it will go back to an idle state. Okay, so it will remain in the heap memory region for the entire lifetime of the network, and will be executed every time you send an activation message. Okay, first let me run again the data theft exploit in order to get the value. Okay, so now we have activated the data injection exploit, and we have told the node, instead of doing this sensing every 10,000 milliseconds, to do it every 5,000 milliseconds. Okay, so we changed the time period. You can see it if I don't think, okay, the red LED is turned on every time it broadcasts a message. So now it does it every 5 seconds. But let me try again to see. Okay. So now, what I want to show is the stop radio exploit. Okay, so you will see that the node will not be able to broadcast its message. Okay. So again, the exploit is being injected. This is a small one, so only 5 packets are needed. Okay, so now you will see that, I think this is visible. So it tried, when it woke up, it tried to send a message. So that's why the red LED is turned on. But because it couldn't actually broadcast the message, okay, it's stuck over there. Okay, it cannot broadcast the message. Okay, so the red LED is turned on, meaning that it cannot send the message. I can activate it again and set the radio transceiver back to active. Okay, so eventually, the next time it will wake up, okay, you can see that the red LED is turned off, so again, it starts transmitting its messages. Okay, so finally, I'm going to show the energy exhaustion. Okay, so this is big, so we are injecting now the exploit shell code. Once it will be activated, okay, we will lose control of the node because it will go into an infinite loop of transmitting dummy buckets. You will see that it will start I have thrown inside the exploit once sending a dummy packet to turn on the green LED, so you will see that it will go crazy. Okay, so I don't know if you can see it, the green LED, it's pretty quick, so, but now it has been in an infinite loop, okay, so it starts transmitting messages. Now also the final thing that I want to say that for each one of the exploit, we keep a history profile, so these are some fancy stuff. You can see how many times you have activated one exploit, you have access to each one of the replies you have received from each one of the nodes. All these replies are stored in an underlying database, so you can have offline analysis. So this was it, the basic tool now. Final, some fair questions. If we have tested tool against real deployed networks, okay, so now the answer is no. But we have tested it against sensor networks inside our lab, but we are pretty sure that it will work against real deployed networks because the same thing happened with our previous attack tool, the Census tool. Okay, initially, we tested it inside our lab, but then we tested it also in some real deployed networks, and it worked perfectly. So with Census, we took complete control of the sensor network. Now, what sensor platform currently is used? As we showed, the T-Mode Sky, okay, which is based on the von Neumann architecture. We know that code injection attacks can also be performed against hardware-based devices. Okay, and we want to investigate how such exploits can be explored against these devices because this is considered a more challenging task. Okay, because you cannot simply copy instructions to the data memory region of the node and then manipulate the program counter to point there and execute the instructions. Okay. What you have to do there, we wish to find a better way of injecting an entire new firmware for the sensor node with a new scheduler and all this stuff. Okay. So being able to inject malicious code without doing it byte per byte, because this is really time consuming. Finally, do software vulnerabilities exist in other network layers? Okay, yes, the radio communication breakdown exploit is the proof because we have used this data variable, okay, the b-shutdown request. We are studying other layers such as the MAC because we wish to be independent from the application layer that actually is the code written by the user. And one other important thing that I didn't know is that I spoke in the break with Travis Goodspeed, which is pretty good in hacking sensor networks, and you can actually use the signals and the signal strength in transmitting a message, and again inject malicious code exploits without the need of any buffer overflow vulnerability. Okay. I didn't know that, but separating a message in layer 2 and layer 1, okay, it's a pretty fancy trick. He told me that he will publish the paper next week, so I strongly suggest to read it, because you can inject malicious code without the need of a memory-related vulnerability. Okay, this is pretty cool. Now, once again, okay, by publishing such a tool, okay, what we want is to explore network vulnerabilities and actually show in the research community that more robust security mechanisms are needed, especially in the case of the new application in the participatory sensing, where we deal with private and sensitive information, because with the use of the mobile phones, okay, we can have access to the personal information and the personal contacts of the owner of the mobile phone. Okay, so performing such spyware exploits against sensor networks that are incorporated in mobile phones, it's pretty destructive. Okay, so we wish to motivate the research community for more secure and robust secure mechanisms. Okay. Finally, we are planning to upload the code. Okay. I think within the month or at the end of August, the code will be available in this link. Okay. So you can go download it. You can define new exploits, upload them to the site. Okay. So you can publish your new exploits with your own names as the authors, or you can find bugs, okay, because obviously the code has limitations. And this was it. Now, if you have any questions. Okay, thank you.